Kia ora koutou katoa. Thanks everyone for coming to the last session of the conference. It's a pleasure for me and an honor today to introduce our fantastic speaker, Ruben Boroschek. Ruben is coming all the way from Chile to talk about structural health monitoring for informed decision making. Ruben earned his engineering degree from the University of Costa Rica and his doctorate from the University of California, Berkeley. He has been a professor of civil engineering at the Civil Engineering Department at the University of Chile since 1992. And he has published more than 300 articles, including journals and conference papers. His work areas of expertise are seismic hazards, experimental dynamics, structural health, monitoring, vulnerability assessment of critical facilities, seismic isolation, and passive energy dissipation. He's a CEO of RBA Consulting in Chile, right? Which includes projects everywhere, including Chile, Peru, Argentina, Germany, Pakistan, Indonesia, among others. Ruben was the director of the World Health Organization for Collaboratory Center for Disaster Mitigation in Hospitals, and over 10 years. And he also was the president of COSMOS, the Consortium for Organization for a Strong Motion Observation System based in the US. He had the opportunity, during this time, he had the opportunity to inspect many hospitals after earthquakes in Nepal, Mexico, Bolivia, Peru, among other countries, where he and his team identify areas of functional and emergency services at different hospitals. This experience definitely influenced his career. Being at places that have been destroyed by earthquakes was not easy, definitely, but made him appreciate even more what he does. When he's not in response mode, Ruben also helped with the planning and instrumentation of many hospitals overseas. Those trips kept him out of the house for more than 3 months a year, and again, not easy. It was very rewarding. Ruben is passionate about understanding the behavior of structures by using data that comes from monitoring buildings. He also enjoys teaching as a good professor and working with the students. I have to say this, on a personal note, I must say Ruben is very kind, humble, and knowledgeable person. It's someone that you really will enjoy have a conversation with. I encourage you all to come and talk to him before he goes tomorrow. And so please join me to welcome Ruben today.
Thank you. Okay, the mic is on. Yeah, let me put the clock here. First of all, thank you for staying for so long. This is the last talk, and it's a pleasure. I want to thank the organizing committee for the opportunity to show some of the work that we are doing on the monitoring sector, not the hospital sector, actually. And it's on structural health monitoring, the state of the structure, hopefully fully autonomous, and receiving the information in your email, your phone, or whatever you decide that you want to receive information on the state of structure. So I'll show you some of the examples. Maybe during the questioning, I can show other things. So that on the upper left there, you see Adobe Church from the 1600s in Cusco. We have been monitoring that for the last 6 years for humidity and tourists walking around the building, and also, of course, earthquakes. And in the center, you see the model of a bridge that has no drawings, and we have to update or create the model only based on sensors, not measuring the sections, because it's on top of a big gorge, so we was not able to inspect directly, and we put around 40 sensors at the beginning. We monitor with some trucks that pass by and we were able to capture the dimensions of all the sections. Later on, like 6 months later, we were able to confirm that the sections that we picked from data were okay. And we have been doing this in the mining sector, mainly in Chile, but also in the electrical sector and in buildings, of course. So all this work is a mixed work of university with a lot of students, also at the office with collaboration with many professors and engineers. So monitoring is for existing infrastructure, and it's mostly on the maintenance side, okay? So in order to maintain a structure, hopefully you have all the design and construction documentation, the maintenance history, the current condition of the infrastructure, all the environmental conditions that the structure is experience, whatever code changes happen, and if you're lucky, you have some monitoring there, and you do something with that information. And I'm gonna stop in the last 3 points during my talk, okay? At least in Chile, we are mandated by law to monitor all dams, any type of dam, mining, water resources, whatever you have. If you have a dam, it has to be monitored for safety. And it has to report to a maximum of 3 days after an earthquake if it's safe or not. Yeah? The 3 days is because at the beginning, these were analog sensors put in the dams, and there was no time to understand retrieve the data and do the analysis. Now it's nearly immediate, as I'll show you some examples. In industry, only critical infrastructure like LNG, okay, and some specific type of structure have sensors in Chile, at least. Bridges, very little, okay? And buildings, only where there is problem, or if it's a hospital that has base isolation. We are now building most of our hospitals, large-size hospitals, 1,000 bed or higher, with isolation, but also with monitoring, because we already have trouble with some isolated structures that user modified the infrastructure, and we didn't realize it before, and during small earthquake didn't behave properly. So this was critical. But it always surprised me why the civil engineers, the structural engineers, are not used to having data of their built environment. Why we always are so reliant on what we did at the design stage. Well, at the university, I'm a professor of experimental dynamics. We teach how to design new structures. We rarely teach how to maintain structure, or more rarely, we don't teach how to design a structure to be maintained, okay? So we just live with whatever we design, and actually we trust our design in such a way that it will never has to be maintained, inspected, or things like that. For example, in the building that you see on your left, you see these 2 columns are critical for this 35-story building. But if an earthquake occurred, that in the case of Santiago, where this building is, that we have an acceleration of 2 to 5% G, at least once a year, maybe twice a year, and 10% G around every 5 to 10 years. Yeah? And if the owner asks you, please go and inspect the building, the first answer is that you will do a walkthrough. But if you see those columns are full of marble, there is no way that you can inspect that structure. There is no way. So you can offer the owner just to remove all the marble. And then he will say, no, I will look for another engineer. So if there were damage, and it didn't express on the surface, there is no way you can control the things. And we don't design for this. We don't design for inspection. For example, this building that I'll touch it again, but it's a 54-story building. The first floor is 14 meters tall, and it's encased, it's a steel pipe with concrete encased columns. So, and everything after finish, everything is covered with marble again. So this building suffered damage during the 2010 earthquake. And the owner asked us, is there any damage on this building? And in order to answer the question without monitoring was to remove all the cladding, okay? And that was not an option. I'll tell you what was the option. But I'll tell you a couple of sad stories. For example, this bridge is in Peru and collapsed last month, okay? Can you inspect for scarring? It's very difficult, especially in non-clear waters, yeah? So how you do this? I mean, you send a guy, an engineer, to inspect the bridge, what he can do. Look at, from the top or with some special tools, but he will not go underwater, especially in this type of river. But you know there is a scouring, but there is no way to control it. And he goes back to the office and said, I didn't see anything, okay? And then collapse occurs. This structure also collapsed last month, killing 8 people. This is the courtyard, the food courtyard of a commercial center. And there were people inside. The owner of the structure knew that the structure had problem. So he sent an engineer to do an inspection. But the roof was more than 15 or 20 meters high. So he just stood on the slab, look upward, and say, okay, the only way to inspect this is to go up and remove whatever covers the main elements, but he didn't do it because the owner didn't pay to do that type of work. So 8 people died. Yesterday or the day before yesterday, 130 people died in a dancing place in Dominican Republic. There is another case that for me is an extreme. It's another building in Santiago. This is like 30-story building or 25-something. And you see a column that is 5-story tall. During the design, the architect asked the engineer to do the thinnest column possible. So the designer worried about, because the overturning is a corner column, okay, did no linear analysis, put a very thin column, put some irregularities in the column in order to capture whatever axial load was going there. And so he ended up with the thinnest column he could develop with the analysis he was doing. Once he finished, the architect saw the column and said, no, this is too thin. I will cover it up with a bigger column so people trust the building. But the engineer didn't change the size of the column. So it's a very critical column designed with nonlinear elastic element for compression and everything else. But when you go there and you see it from the side, it's very thin. It has gone through 2 earthquakes, design earthquake, 0.4 to 0.5 G at the ground. No inspection done. Because in order to do the inspection, you have to go 5 stories and remove all this cladding. They are not willing to pay for that. Yeah? So here, monitoring is very important. And we are not designing for inspection, except on some structures, as I mentioned there, LNGs and some industry, but very little. Yeah? Think on that. Why we're doing this? We are not going to monitor all the structure, but we are not going to design for you to inspect easily a structure. Okay? So we have some problems there. So in some structures, as I'm going to show you some examples only, we do monitor. Okay? So hospitals, dams, as I said, some key bridges, and maybe some industry. The idea is to put sensors. Any type of sensors that give you an answer to your damage scenario. Strain gauges, pressure cells, displacement, tilt meters, accelerometers. That should be sent to a computation center. It could be local or remote, depending on your resources and the conditions. And then that analysis should be sent to you in a manner that is understandable for the person that is receiving the information. It could be a simple street light or very detailed data if you are engineer knowing the structure that you are doing. But it has to be fully automatic. We cannot do it manually. And this is a structural health monitoring. If you don't do it automatically, it's just monitoring. The standard things that we did maybe in the 50s or the 60s, okay? But if you are gonna do it fully automatic, then we will call it structural health monitoring. And what type of sensors are you using? Well, we are using sensors that can send data. It could be wire or wireless, whatever we want. And it could, at the beginning, we started with very expensive sensors on your left this time. So these are very expensive, maybe $1,000 or $5,000 per channel. But now we have these MEMS sensors for accelerometers and other stuff that are very cheap, $50 or something like that now, okay? And the thing I want to show you, as an example, is that we can use cameras now, video cameras, as a sensing instrument. And of course, the drones and things that were explained during the presentations earlier during the Hualien earthquake. So now we have a huge amount of sensors that we can use to detect what's going on a structure. So let me stop here for vision sensors. So just for those that don't know, image is just a matrix of intensities, okay? So it's like having a matrix, and the intensity is a number. So I don't know how to treat a video, but I know how to manipulate matrices. A video is just a sequence of matrices with numbers in it, okay? So what I do now is take, for example, the red rectangle that you see there, it's a chimney of a castle, and then I can represent that as a surface. And in the surface, I can get the maximums, the surrounding areas of that number, and get eigenvalues and many other things that we like to do with matrices. So that's what I'm gonna do. And the nice thing and the opportunity here, sorry for some videos are from earthquake, but there are cameras everywhere now, okay? So imagine that in those lists I put there, this is the number of cameras per square mile, okay? 7,500 cameras per square mile, yeah, in some Chinese cities. But typically, we will get at least 20 or 100, okay? Actually, if you are in Japan, I have seen the news when they can follow a person all the time except on the bathroom. That's the only place they don't see a person when they want to track him, okay? So why don't we use this information? We have to just learn how to use it. So on my sabbatical 2 years ago, I went to Tokyo University, and I asked Professor Kusunoki to give me a video of a test in e-defense. But just the videos, not the data, okay? So Trevor Yao helped me, he's from New Zealand, helped me with the data. He sent me the videos, and in a month, I came back with what I can take from the videos, okay? So these are the videos. So I take the videos, I do some stuff that I can tell you if you are interested, but I can get information on the motion of the system. Those green dots you see there are just fictitious sensors. And I'm using a technology that was developed in 1960 to capture those motions, okay? So with doing some manipulation of these many green dots, you get the traces of the motion. If I get the difference between the traces on 2 floors, I get the interstory drift. In that figure you see in the middle, there are 2 lines, one green and one blue. They're quite the same. I didn't compare them myself. I gave it to Trevor Yao. So then this is the interstory drift for this building. The error was less than 1%, okay? Not only that, I calculated the acceleration of the floor just based on the video. And the error, you can hardly see it on the bottom figure. So we can convert any video, any pixel in a video to a sensor if it has certain characteristics. And we have so many security cameras. For example, these videos from Thailand. I just did it 3 days ago. So I download the video. The left one is the original handheld video taken by somebody. You can see a red arrow on the bottom, how it moves around everything. The center video is that I take the video and I center the matrices so it doesn't move in some areas, okay? After that, I stabilize the video. You can see the boundaries changes. I zoom in any part. In this case, I zoom in the upper part bridge, and I just put markers, or I select some pixels that have special properties. In this case, they are in the same line of the bridge, so I can capture the opening and closing of the system. So if I now know the dimension of the bridge, I know how much it opened. But not only that, if I take the video of the cable stay bridge in Thailand again, on the left side, you see the original video, and some yellow traces is the handheld phone. And I take that video, stabilize it, and then I get a stable system. You see it doesn't move anymore on the ground, but the bridge keeps moving. And I zoom in any place of the video, and I have so many sensors now in that structure that I can actually get the time history. We haven't any sensor on the structure, okay? I'm just using security or handheld cameras. And then I can do all my system ID that I know how to do it. It's very hard to use handheld cameras during earthquake, but there are so many cameras. So for example, in this case, in this building in Santiago, we have web cameras, $15, okay? That's the cost. But it's a bullet camera that doesn't vibrate during the shaking. So during the earthquake, it's looking at a tube mass damper, very short length tube mass damper, but I can trace the motion instantly using just the video. No cables, no energy, except for the video camera. Okay. Also, we have the option with these videos to have drones. So what we are doing now is flying drones around buildings, flexible buildings, and or bridges, and actually we can get mode shapes and frequency from the video from the drone. Okay, so it's possible just to fly around, and if the structure is flexible enough, we can capture. On the top part is the drone video tracking, and in the center is the frequency, and the vertical lines are sensors that we put in the building to have the ground truth, the real value for the frequency, and the error is less than 5%. But I didn't have to ask permission to monitor the structure. I just needed to fly around the structure, okay? With the Baha'i temple in Santiago is a crystal structure, very tall one. It's base isolated. So we offer them to install a drone, self-controlled drone. It parks itself, it charges itself, and has a flight pattern defined by us. So we can fly the structure automatically, get the pictures whenever, as frequently as we want, create a 3D model of the Baha'i, and also the security cameras inside are looking at the ceiling, and I can trace the vibration of the ceiling without having to install anything. Or more important, I don't spend money in maintenance because the security cameras are maintained by the owners of the structure, okay? So it's a tool that is not the solution for everything, but it's contributing a lot to what we're doing now. Okay, so forget about videos, it's just a tool, okay? It's not the center of my talk, but some example of decision taking based on data. Okay. So during the construction of this 54-story structure, it was the first building 200 meters tall or higher in Santiago. So the owner of this building, that is an architect, hired us to monitor the construction to validate the design model of the engineer. Okay? The engineer was very happy because he's very open to observations. Okay? So he didn't have any problem monitoring. Other people have a bad reaction to monitoring because they will be confronted with reality. And when reality and modeling doesn't match, they have to explain things. Take time to explain things, and maybe they don't know the answer why they don't match. Okay? So that's a problem that we can discuss. But in this case, we set up a program of monitoring with a few sensors that will give the properties of the structure automatically every 15 minutes. Okay? So every 15 minutes, we know what was the structure. Nobody was touching anything. So in this, on the left, you see lines that are going down. On the bottom, the x-axis is time, okay, days actually, okay? And on the vertical axis is the frequency, the inverse of period, is the mode shape, the lower line, is the first 3 mode shapes of the system. So we monitor the system every 15 minutes for 2 years, okay? And of course, the designer said, you're crazy. I cannot even open my email with all the data you're covering. I just want to know if the model fits reality or not, okay? So every week, we cut the structural design model, not a digital twin, just the design model is called pre-digital twin model. I mean, just the design model of the structure. And we compared it with the data, and it was very interesting because you see first mode and second mode there. The first mode, and there are 2 lines, red and blue, and one is the model, and the other one is the real data, the real period of the structure. The second mode had a problem. Just at the start, when we were in floor 6 or 7, I don't remember. So something happened, we detected the problem, we sent the information to the designer and to the owner. They're quite open. So they sit and take a decision. They realize why there was such a big jump on the period. It was a torsion problem not considered at the design level. So the options were we demolish, or we evaluate the condition that we have now, and we project what's going to happen with this building when it's finished, okay? And then we decide if we demolish or not. And in this case, they didn't demolish, okay? And it was finished just as a different structure. But it was known, and the data was there to take the decision. This instrumentation was taken out on January 2010. On February 2010, the 6th largest earthquake in the world occurred, okay? And this building got damaged. All the balconies, okay, on the top part of the building fell because this building is 200 meters tall, actually amplified motions in vertical direction, not only horizontal. Even for a small earthquake, you can notice how the building is actually elongated in the vertical axis. So amplifies a lot, okay? And the owners called us because he said, okay, can you tell me if the building is damaged or not? I said, the first action was, please inspect all the intersection of the column with the slab. Okay, you have to remove all the ceilings for inspection. No, you don't do that. It will be too costly. Okay, but we have data, very detailed data, okay? So we came to realize that we have enough data to say that there was no damage, and nothing was done except repairing the balconies and non-structural elements there. Okay, we have been monitoring continuously structural health monitoring since 2009, okay? So nearly 16 years now. So what you will see here is for a 9-story structure, again, some lines, not in color lines, but look at the bottom 3 lines. There is like something slide down in right there. That is the occurrence of the 2010 8.8 earthquake. So, and these lines are natural frequencies, so the inverse of the period. And this building suffered a drop of frequency that we capture in less than 10 minutes and communicate to the owner. That is us, because it's the faculty of engineer, okay? And we know it was damaged, 20% drop in stiffness. So in periods, so 40% drop in stiffness. So after inspection, it was decided that it needed paint. Okay? There was no retrofit or any repair. And this is a 1960 building, and we know it behaves properly. So at least we know exactly what happened during the earthquake. You see all the frequencies drop, each mode in a different way. But you see the lines are not completely straight. Actually, the lines have shapes that are associated with seasonal changes. Temperature, humidity, the sun position changes the period of the structure, okay? Not only that, if it rains or it doesn't rain, we have changes. That are as much as you see it there. And of course, if there is an earthquake, there is a change. So one important thing that we learn when you're doing structural health monitoring is that the structure is not your design model. It's not a fixed parameter system. Actually, on the top here, for example, is the first mode with the seasonal changes, just summer, winter, autumn, spring, okay? And the changes is around 5%, okay? 5% period change. Mode shape doesn't change so much. On the second line, on second graph, you see in blue the temperature outside, but scaled to a normalized value. So when you have high temperatures, the period elongates or the frequency goes down, okay? And you can see that on the third plot when we twist or overturn, multiply by -1. But the important thing that we realize is the daily changes. On the first line graph, we have the first mode in orange, and blue is the temperature. Sorry, the other way around. Temperature is orange, blue is the first mode, or the second and third on the line. So what we realize in this building is that there is a change between 1% or 3% just for a temperature change in the structure, yeah? And that change is not instant. So if I now comes here to be 24 degrees Celsius, maybe in 2 hours, the building will be flexible enough. But it depends on the time of the year, because sometimes we have the sun on summer on top and in winter on the side. If your structural system is not facing radiation or the sun, then you will have a different pattern. We have done this in many buildings, and it's completely structure dependent. What's the range? 1 to 6 or 7% of period change just because environmental conditions, normal conditions. But we have earthquakes. In Chile, we have a magnitude 4 every 4 to 6 times a week. So we can use that data, small shaking, okay, to analyze the changes in the structure due to amplitude. So quickly, because I'm taking too long, so we do an analysis every 4 seconds, and we get a response like this. This graph is the same building. The red part is the period in the vertical axis, and the horizontal axis is the drift of the structure. So what are you seeing there? The red, for example, is that depending on the level of deformation, the period of the structure changes, but it's linear elastic. I mean, it deforms, elongates the period. When the earthquake is gone, then it comes back to the original. You have a small earthquake, a small period change. You have a big earthquake without damage. You have a change that is 10%, no damage, okay? The stars you see there is due to the earthquake. So red is pre-earthquake data. Blue is after 2010 earthquake, meaning that the period change was 20%, and the pattern of change completely changed during the earthquake. The stars are 4 seconds of earthquake time. The lighter ones are the beginning of the earthquake, and the darker ones are the end. So we can track completely how the damage occurs on the structure. Okay, so how we use this? Well, the first thing is you need a lot of buildings instrumented. So one thing is to use camera. We are not going to talk anymore. But what we're doing is using cheap sensors. Only one sensor in a building, on the top, for example. And we can trace deformations we don't have the base, so we have a problem there, but we more or less know a little bit of amplitude. If we have a sensor close by, we can do some type of information. It's very cheap. It's less than $1,000 actually. And we get very good data on the period, okay? And we can track a change of state with a simple sensor on the structure. And this, we have like 40 or 50 of these structures. So many of the work we do is just with data. And this is important. For example, we have to, in the left side, there are some blue traces. It's a train passing, it's a subway train. So we were hired to tell the owner which wheel was not rounded enough, okay? So we put sensors on the rail, the train passed by, so we get the vibration, and we're able to tell is the third wheel on your left that is having problem. We don't have any model. We are not the mechanical engineers. I'm a structural engineer, okay? But we are able to pinpoint just with data which is the wheel that is having problem. On the right side, you see a huge mill. I'll show a little bit more of that. That is having problem at the foundation level. Only with data, we can tell what's the stiffness and the change of stiffness of that structure. So I'll show you some example of data-only information. Okay, this is a suspension tank of a very thick sand coming from the mining project. You can see a person installing the accelerometers. It's a huge, huge tank. The problem was that in certain conditions, the tank vibrates so much that the bolts are getting loose, okay? So it's a resonance problem. But what is the resonance? I can do a model, but doing a model with a tank that the fluid level changes and the density changes, and there are some fans agitating or moving the water is very difficult. So forget about that, just data. So I put the sensors, monitor when, at which level, and at which this density of the liquid we have resonance. So I capture that areas of resonance, and I tell the owner, don't stay in this position too long, because resonance is a building process. You need time to build huge deformation in resonance. So you capture that you are amplifying the deformation with the sensor. Immediately you tell the owner, get out of this stage, and you do it automatically. Okay, you don't need an operator decision looking at a graph, but you do it only with data. In this case, we have a main mill. It's called a SAG mill in a mining project. The dimension is nearly 14 meters, and the foundation was cracking. So they asked us, can you monitor? We will repair it. Can you monitor that the crack is definitely repaired? So what we did is instrument the foundation, and just with data, monitoring prior to the repair and many months after the repair, we were able to tell them, okay, the repair is working and is safe and we remove the instrumentation. So no models, okay, just pure data. Sometimes we have some models, and this model allows us to predict things. And so we pass from a diagnostic case, just pure data, we can say something happened, but with models, we can predict what's going to happen in the future. Or better, we can predict responses in places that we don't have sensors, okay? So in that case, for example, it's a wharf, a very small wharf, so they hire us to monitor the wharf for burden impact, overloading on the main slab, and current scouring of the system. So we install in system, and just with the data, we learned in 3 or 4 months what was normal, and with the model, we tried to pinpoint where the damage was in case it was needed. The same for the building I show that we monitor during construction. These are the signals, and that's the monitoring. So the port, we were able to install some sensors, let the data run, learn what it was meant to, for example, when the tide was high or lower, what was the natural period, And after a few months, 2 or 3 months, we can set alarm and, or alert levels, just with data. But also with the model, we know more or less what's going on. The other extreme is to have very good models, digital twins, really. These are really digital twins, that I can fuse data and modeling. And with that, I can do things that are pretty amazing. This is a 700,000 elements on the top for the Cathedral of Santiago, and a building on the bottom is a 60,000 element structure. Everything has been adjusted according to the data. It takes a long time. So I'm going to stop on this example. This example is a hotel building, administrative building, and a casino building in the middle of a mine, in the middle, 20 meters from the blasting areas. So the contract that we had in this case was to monitor the building, keep it safe, install instrumentation, identify. They will blast every 2 days for 2 years. There was some problem with the construction of the replacement building got delayed. So in order not to stop production of they decided to monitor the building, and every time there was damage, they will repair it. So our job was put the sensors, detect the blasting, and in 30 minutes, they should have drawings where the most possible areas of damage occur, and they will have another crew by another company that will repair it in 1 hour if it was a mild damage, or they will stop process if it was a big damage. And we did this for 2 years, and he actually won a prize for being able to do this, because we have an controlled earthquake, so it was more easy. So the amazing thing is the accelerations on the building were 2 times gravity, 2G. Okay, it was not a very small shaking, it was a huge shaking. So how we did this? It's a mix of data and models. Okay, in this case, we got structural models, linear and nonlinear, and we did fragility studies and vulnerability studies. We monitored the blasting, how the blast went on the ground. We input it into the model, and we established fragility curves depending on the scale of the blasting. So we have like a street light, green, yellow, orange, and red, that will go to the client because he doesn't understand what we're doing, actually, but the street light was clear. And so we developed the system. We have several models on the cloud. We have sensors on the ground. This very redundant system. Every time there was a blast, it was recorded, the data inputted into the ground. We sent it to the cloud. Many models were running. And with the data, we evaluate if damage or change of state occurred. With the model, identify where the damage could have occurred. Okay? And drawings were developed automatically. And all the floors were marked in a special code. And we know all the elements. All the elements have a street code, and we send the report in less than the 30 minutes that was our maximum time. Yeah, and fully automatic. And they pay us 24/7 engineering, because it's not only for blasting, also for earthquake. Because the building was weak, there were 300 people working on in that building, so it was very critical. And after 2 years, the building has to be demolished, as you saw there. So this was fully automatic. We just monitored that things were going on. And the decision was taken like this, and it worked perfectly. Actually, they augmented, have a higher increase in production. So this is one of the things that they were worried that they could not produce because of the building. They cannot operate without the hotel because the people sleep there. I mean, the workers sleep there. Okay, so this monitoring helped them to keep the building. Also, we were able to identify when the blasting sequence increased the damage, so we modified the blasting sequence, the time between blasts, small blasts, and at the end of the project, the building never got damaged. So they were blasting very close to us, but the sequence was scheduled in such a way that the blasting didn't affect the structure. But in order to start closing because 45 minutes is hopefully my presentation. I want to say that it's not magic. Monitoring is not magic, and there is an excellent example from Francisco Carrion, Mexican transportation, that he was asked to monitor a cable stay bridge that their cables were snapping, okay? So the condition was that he will detect the snapping and give an alert, okay? So he put a lot of sensors. He knew the scenario, snapping of the cable, okay? And in the center, you see a graph, and I don't know if you can read there. Sorry for that. But in this part, you see the timing. So this is the initial snap of one cable, and these are the other cables snapping, okay? The time between the first cut of the cable and the last one is seconds, okay? So in this case, structured health monitoring has no sense. No, it's nonsense, because how are you going to give an alarm that it will tell the owners, the users, that you have half a second to run away from the bridge, okay? So this is what Carrion and colleague stated in their conclusion. Be careful. I mean, there are things that are too quick for you to react. So monitoring is an excellent tool to understand things. When you use it as an alarm system, then you must be very careful. You need to prepare not only to receive the data, you need to know what to do with the data, yeah? And how you're going to react. And this is the most critical part that we have experienced. Many people, the port people, the people from the ports that we were monitoring, it was a time that they said, don't send us any more information. We are not able to read it, and it's on our desk. If you put in that report that something is wrong, and it's on my desk and I didn't read it, then it's my responsibility. I prefer not to have that information, yeah? And so we realized that we were producing too much information, okay? And it's not possible for a human to solve it. Of course, now we have AI and everything else, but you have to act. And this is the main thing I want to leave in this talk. I mean, we have all these tools, but if we're gonna want to react, we have to be very careful. So here we have three things I always consider. The cost, okay? You have the initial cost. It's very cheap compared to the benefits, in my opinion. For example, one channel of a good accelerometer is $1,000. From a MEM is less than $12, okay? The buying of the thing, well, you need some administrative stuff to buy it. Installation generally is between 2 to 5 times the value of the sensors, okay, more or less. Then you have to pay for maintenance, okay? And if you have a very expensive and robust sensor at the beginning, your maintenance will go down. But if you have cheap sensors, your maintenance will go up. And it will depend on you how you balance. If your personnel is close to the sensors and installation and is low-cost personnel, then go with cheap sensors, okay? But if you are far away from the infrastructure, you better have very good sensors because you don't want to maintain. The other thing, two costs is operation. You don't not really need to maintain it, you need to operate the thing. You have to do something with the data, okay? So you have a center for recollecting the information, okay? Then you have operators taking decisions. And the other thing that it has cost us in one mining project, very important cost, is what I'm gonna do if I receive an alert or an alarm condition. So how I'm gonna react? How many people I have to have? Where I should have them? Okay? What resources they need, okay? So now we can do many things with instrumentation, but be careful. It's not the cost of the sensor, unless you just want to gather data for knowledge and improve codes and whatever, okay? That's a standard thing we do, yeah? But if you want to use it as a part of a process, maintenance, an operation of a system, you have to now follow the whole thing. You don't want just information, okay? You want information that you can handle, that you can react in a proper way, so you can really help the system. For me, having data is always beneficial, but if you are the responsible person, sometimes it's not right what I'm going to say, but it's better not to know. Yeah? And if you have been in a condition that you have to take decisions, and they give you a pile of information and you have 5 minutes to take a decision, you get into trouble, okay? And I don't want to be extreme, but in the practical side, you have to know, balance your abilities with the data is coming to you. I prefer to have a lot of the data and then take a good organization and a good response to use this data. And that's it. So just want to say, going back to the videos, that is my passion for the moment, is that the video itself fully is a sensor, is a virtual sensor. In this case, the same bridge, instead of looking for points that are clearly marked, I just take all the edges and I track them. And the nice thing about this is that now I have mode shapes and everything. I have to correct for perspective distortion and many other things that occur in the vision condition. But now I can have a lot of information. And I think in the future, we will have a mix of videos and accelerometers and strain gauges giving us a lot of information, but it will have to be processed by some artificial intelligence and will give us messages that are easily for us to handle, okay? And or at least we will be prepared to handle. Thank you.
Thank you very much, Ruben. Some questions from the floor, if we have any. Over there.
How accurate is the videos in terms of getting the measurements, looking through floors, that sort of thing?
As accurate as the conditions are, it's better than nothing. Sorry for being so blunt, but if I have the video, at least I have information. But if it's a handheld, I can do it a centimeter or less, okay? If it's a fix, for example, in the tube mass damper, I can get a millimeter even less if I have many points, because when the earthquake is shaking, the camera is also shaking. So it's just the relative motion between the two that I'm capturing. So 1 millimeter or something like that. There is a technique called vision microscope that was developed by a Google researcher, okay? And actually, I don't know if you have seen this, but if you have, for example, a bag or something on the table and you film it and you magnify the motion, what is called phase magnification, you can record your voice from the vibration of a glass or a bag or a leaf on a plant that is close to you. I mean, it's very precise, okay? But depends a lot on the conditions. It's an additional tool, okay? For example, in a lab, a high impact lab in the northern part of Italy, the only sensor possible when they are doing high impact load is vision. There is no sensor capable of resisting a blast. So they monitor all the particles using just vision. Is something more precise than that? Yes, but we don't have it. We cannot use it. So it's a tool. Yeah. And you have to recognize it's not perfect. I prefer an accelerometer in terms of precision, but if I don't have it, good. I'll have less than 10% error if you want a gross number, and if you do it right.